Today we're going to look at two problems from a math contest that Duke University puts on for high school students known as the Duke Math Meet. And one of these problems is fairly early in their exam and the other one is fairly late. And the first one we'll look at is from the year 2017. So our goal is to find the largest possible natural number m so that we can find a list of m natural numbers, I'll call them a1, a2, up to am, such that a1 factorial, a2 factorial, all the way up to am factorial, all end in the same number of zeros. Okay, so let's maybe observe that what we're really looking for is the number of times a 5 can be divided into, well, a1 factorial, a2 factorial, so on and so forth. That's because every other number is even, and so you have plenty of even numbers to multiply to each multiple of 5 to create a multiple of 10. So really, the number of ending zeros is going to be exactly the number of factors of 5. But observe that a factorial picks up extra factors of 5 as it moves, through the natural numbers. So observe that 5 factorial, 6 factorial, 7 factorial, 8 factorial, and 9 factorial all have the same number of factors of 5, whereas 10 factorial has one extra multiple of 5. Okay, so keeping all of that in mind, how can we write this down carefully? Well, I'm going to use the pigeonhole principle here. And, well, in order to do that, it's going to go something like this. So let's observe that if m is bigger than or equal to 6, then by the pigeonhole principle, there exists, let's see, an AI which is bigger than an AJ such that AI is congruent to AJ modulo 5. So why did I pick something mod 5? Well, we'll kind of see why that'll work. But after choosing this modulus of 5, well, there are exactly 5 residues mod 5. So in order to use the pigeonhole principle, we need to choose, well, 6 or more pigeons to fit into these 5 pigeonholes. That means we're guaranteed to have 2 pigeons. In this case, the 2 pigeons are the 2 numbers in the same pigeonhole. In this case, the pigeonhole is the residue modulo 5. But now, well, what does it mean for AI and AJ to be congruent mod 5? That means that 5 divides AI minus AJ. But, well, what does that mean? Well, that means that AI minus AJ is a multiple of 5, so we can write it as 5 times K. And I'd like to observe that AI is strictly bigger than AJ, so that means that K is in fact bigger than or equal to 1. Well, observe that that means that we can write AI as AJ plus 5 times K. But then that's going to be strictly bigger than, or I guess I should say bigger than or equal to, AJ plus the number 5. And that's just, well, it's most of the time it's strictly bigger than if K is strictly bigger than 1, but just assuming that we have the possibility of K being equals to 1, we get equality here. And now we're kind of ready. So now let's make the following observation. So we're going to observe that AI factorial is bigger than or equal to AJ plus 5 factorial. But that's going to be equal to AJ plus 5 times AJ plus 4 times AJ plus 3 times AJ plus 2 times AJ plus 1 times AJ factorial. Okay, so why did I spread all of those out? Because now observe that we have 1, 2, 3, 4, 5 consecutive numbers, and we're taking the product of these 5 consecutive numbers. So now let's observe that, well, at least two of these numbers are even. Well, we could either have aj plus 1, 3, and 5 even, or we could have aj plus 2 and 4 even. So in other words, this is an even number. Well, let's maybe take this just to make sure we see this is most definitely even. Then, well, let's also notice that it's a multiple of 5. And that's because if you take 5 consecutive numbers, you're most definitely gonna get a multiple of 5. So if aj plus 1 is a multiple of 5, then we're done. Otherwise, well, one of the next ones will be a multiple of 5. So let's write this here. So, and a multiple of 5. But anything that's even and a multiple of 5 is most definitely a multiple of 10. Okay, so if this is a multiple of 10, then we can write it as 10 times a new number. Maybe I'll call that new number n times aj factorial. Okay, but now observe that ai factorial has at least one more 0 at the end of it than aj factorial. And that's just by this product right here. So in other words, the number of ending zeros in aj factorial is strictly bigger than the number of ending zeros in ai factorial. Okay, and that occurs any time that m is bigger than or equal to 6. So, well, what does that tell us? Well, that tells us the possible m values are 1, 2, 3, 4, and 5. So now we just have to find an example that exhibits 5 being a possibility, and we're done. So maybe we'll just write that here at the end. M equals 5 works. And in fact, there's tons of examples to show that m equals 5 works. For example, 5 factorial, 6 factorial, 7 factorial, 8 factorial, and 9 factorial all end in a single 0. Well, and then you could go to 10 factorial, 11 factorial, 12 factorial, 13, and 14 factorial. Those end in 2 zeros, and so on and so forth. Okay, so going back over here, find the largest possible m. Well, that largest possible m is 5, because up here we showed that, well, it can't be 6 or bigger. Okay, good. Now let's move on to this second problem. Okay, so let's look at this second problem. So let's set s equal to the set of natural numbers between 1 and 2 to the 20, satisfying the following condition. So the natural number is equal to 2 to the m plus 2 to the n, where m and n are not equal. Okay, so let's start with a quick observation, which will allow us to write down maybe another conditional version of s that's easier to work with. Okay, so let's observe the following. So we take 2 to the 19 plus 2 to the 18, and we'll observe that this is equal to 2 to the 18 times 2 plus 1. That's just factoring out that 2 to the 18. But then observe that that is strictly less than 2 to the 18 times 4, because 2 plus 1 is, well, it's less than 4. But then that's going to be equal to 2 to the 20. So what we have here is 2 to the 19 plus 2 to the 18 is less than 2 to the 20, which tells us that 2 to the 19 plus 2 to the 18 is in fact an element of S. And observe that this 19th power of 2 is in fact the largest possible power of 2 that we can use to forge a member from S. That's because if we've got something larger than 19, like 20 here, then if we add something to it, we go above 2 to the 20. So I think that's pretty clear. So now we can write S as follows. So this is going to be everything of the form 2 to the m plus 2 to the n, where 0 is less than or equal to n, which is strictly less than m, which is less than or equal to 19. Okay, nice. But now we can easily count the number of elements in S. So the cardinality of S is, well, how do we do this? Well, we choose two numbers from the set from 0 to 19 that are not equal. But there's exactly a way to do that, and that is with a binomial coefficient. So this is 20 choose 2. That's because, well, there are 20 possible values to choose, 0, 1, 2, 3, up to 19, and we're choosing exactly 2 of them. Okay, so what's 20 choose 2? Well, by definition, that's 20 times 19 over 2 factorial. That is pretty easy to calculate to be 190. But next up, in order to get ready for our next step, I'd like to look at the powers of 2 mod 9. Okay, so we can do that by filling in the following chart. So we've got k on the top and then 2 to the k mod 9 on the bottom. And you might say, well, why am I only going between 0 and 6? And that's because Euler's theorem says the following. Euler's theorem being the generalization of Fermat's little theorem. That'll say that the exponents work modulo 6. In other words, we have 2 to the 6 is going to be congruent to 1 mod 9. That's because phi of 9 is equal to 6, where phi is Euler's totient function. Now, we don't actually really need that here because we can just use the chart that we're building, but this at least tells us where to end the chart. Okay, so now let's make the calculations to fill this chart in. 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, but observe that 16 is 7 mod 9. 2 to the 5 is 32. Let's observe that that is 5 mod 9. 2 to the 6 is 64. That's one more than 63. So that's 1 mod 9. Okay, so now let's get to the calculation that we need. So let's take an element from S. Observe that that's going to be of the form 2 to the m plus 2 to the n, where m is strictly bigger than n. And, well, we can write this as 2 to the n times 2 to the m minus n plus 1. And that's just by factoring out that 2 to the n, kind of obviously, because we chose n to be smaller. But now let's observe that we want this to be divisible by 9, in other words, congruent to 0 mod 9. But now this is congruent to 0 mod 9 if and only if the thing in parentheses is congruent to 0 mod 9. That's because this 2 to the n is a multiple of 2. You're never going to get a multiple of 9 out of that, or even like a multiple of 3 out of that. So then, like I said, we need 2 to the m minus n plus 1 to be a multiple of 9, but then maybe adding -1 to both sides, or subtracting 1, or adding 8, or using the fact that minus 1 is congruent to 8 mod 9. This means that we need 2 to the m minus n to be congruent to 8 modulo 9. Now we go up here to this chart and we notice that 2 to the m minus n is congruent to 8 mod 9 if and only if m minus n is congruent to 3 mod 6. So here we have m minus n congruent to 3 modulo 6. But then, well, what does that mean? That means that m can be written as n and then plus 3 plus 6 times k, where k is bigger than or equal to 0. That's just by the definition of congruence modulo 6 in this case. Okay, and now using that condition, we can pretty easily enumerate all the possible values of m and n, which we'll do to finish this off. So we just got down to this condition that 2 to the m plus 2 to the n is congruent to 0 mod 9 if and only if m is equal to n plus 3 plus 6k, where k was bigger than or equal to 0. Now from here, what we'll do is work through all possible values of n, and then after we work through those, or as we work through each of those, we'll find the corresponding possible values of m. Okay, so let's notice for n equals 0, that comes along with a couple of values of m. So notice m could be equal to 3. That's if k is equal to 0. It could be equal to 9. That's if k is equal to 1. And it could be equal to 15. That's if k is equal to 2. Observe that k cannot be bigger than or equal to 3, because then we would achieve a power of 2, which is larger than 2 to the 20, which puts us outside of S. Now, let's keep going. So if n is equal to 1, that means that m could be equal to 4, 10, or 16. And now let's skip a couple and get to the point where n is equal to 4, which means m could be equal to 7, it could be equal to 13, or it could be equal to 19. 19 being the largest possible value for m. So that means that something changes when we move from n equals 4 to n equals 5. Notice if n is equal to 5, m could be equal to 8 or 14. But you can't add another multiple of 6 because you would get 20 and you would get outside of our set S. So then we keep going for a little bit, and we end up here at n equal to 10, which means the possible m values are 13 and then 19. And now, well, let's block these off a little bit. So notice that all of these that I'm blocking in this first green box correspond to 3 choices for m. So notice that we've got 5 choices for n, and for each of those choices for n, we have 3 choices of m. That means that, well, inside of this green box is exactly 15 numbers. And then, well, let's move down to this blue box. So how many choices of n are there? Well, we've got n from 5 to 10. So that's going to be 6 choices of n. And then after those 6 choices of n, we have 2 choices of m. That means in this setup, we have, well, how many total? Well, 12 total pairs of m and n. And now, well, we just have to move for larger values of n. So notice if n is equal to 11, that means that m is equal to 14. And that's the only possible value of m, because if you add another multiple of 6, you'll get larger than 20, like we said before. And then this goes all the way up to what? Well, it's going to go all the way up to 16. And 16 corresponds to a possible m value of 19. Okay, so notice that how many possibilities do we have here? Well, we just can count from 11 to 16. So that's going to give us exactly 6 possibilities. Okay, so now putting this together, how many possible pairs of m and n will give us divisibility by 9? Well, we have 15 plus 12 plus 6, that's 33. So that means 33 elements of S are divisible by 9. That means our probability is 33 divided by the number of elements in S, which was 190, making that our final answer. And that's a good place to stop.